How's it going? Today I want to talk about complex numbers in polar form. Basically what it is we've talked about points, being able to plot them in polar form versus rectangular. We've talked about imaginary numbers, complex numbers like 3 plus 2i. Well, now we're going to put complex numbers in polar coordinates, okay? It sounds harder than it really is. It's kind of technical, but you're going to find it actually is a fairly simple process. So before we can really talk about putting them in polar form, it's very helpful to actually plot our polar coordinate or our imaginary numbers in what we call a complex plane. Basically, we have like an x and y axis going on, but instead of an x-axis, we now have what we call a real axis. Okay, we change it to a real, and then instead of the y-axis, that's now our imaginary axis. So plotting the number 3 plus 2i, is really just a matter of going 3 on the real axis and then 2 on the imaginary, and that's where the point 3 plus 2i would be. Likewise, the point 4 minus 3i would be right 4 on the real number and then down 3 on the imaginary axis, and that's where the point 4 minus 3i. So it works just like, missed that little, there you go. But that works just like an xy axis point. The point 2i would be a purely imaginary number, so that point would be purely right on the, what looks like the y-axis, but it'd be on the imaginary axis. And we can have just purely real numbers on the real axis, so the point -3 would just be left 3 over there. Okay, so we can plot those points. And as soon as you do that, as soon as you take points, like we'll plot the point 3 plus 4i, okay, which would be right 3 and then up 4, right? So as soon as you plot that point, well, what we can now do is, and what that creates is it creates a very specific line that goes out to that point. Okay, we call that a vector. And that vector is going to have a very specific length, or what we call a magnitude, and a direction, right? And yes, I kind of came prepared, but yes, that is the essence of this. One of my favorite little quotes here, or little scenes.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, as I'm committing crimes with both direction and magnitude. Oh yeah!
One of my favorite movies. But anyway, so when we start talking about a point having a length or a magnitude and direction, we can start putting that in polar form, because that's really all polar form is a direction, basically our angle measurement, right? And then a length along that, or our magnitude. So we can change numbers like this into polar form. This is how we actually denote the length of that vector z, right? So we would call the length of that vector, and it actually is going to be equal to the absolute value of a plus bi, okay? Got the I there. Now, basically, we just got to be able to find the length of that. And finding the length of that is actually a very simple process, because we already know how to find the length. If we have any point a plus bi, well, that means we're going to go right a and up b, and we're trying to find the length of that, basically our radius, right? Like, this is the same drawing we've dealt with all year long. Well, when we do that, the absolute value of a plus bi just simply becomes the square root of a squared plus b squared. It's the Pythagorean theorem, right? So if we want to find the length of this, or r in this case, we just simply use the Pythagorean theorem. Okay. And then we actually can start talking about direction as well, because all our trig functions fall into line. We can use sine of theta. Sine of theta is just going to be opposite over hypotenuse, or b over r. Cosine is going to be adjacent over hypotenuse, a over r. Tangent is going to be b over a. And then this actually is going to help us, because what we can do is we can butterfly here, and we know that b is nothing more than r times sine of theta. And again, butterflying over here, we get r cosine is equal to a. And then we can use this one again to help find our angle. So these two rules right here, that b is going to be equal to r sine and a is going to equal r cosine, that actually is going to help us be able to convert. Because the one main thing that we have to be able to do here is the main objective here is to be able to take a imaginary number in rectangular form, and then to be able to put that into polar form and vice versa. Okay, basically we just want to be able to go back and forth. These are going to be the rules that allow us to do that. So basically what it does is we can take this imaginary number, a plus bi, and because we have our rules here, right? Because we have our rules, basically what we can do is we can say this a plus bi, well, that a is nothing more than r cosine. And then the b is nothing more than r sine. Okay, times I. Well, this technically is now into polar form. Now, it's not really in standard form because it kind of looks ugly. We can simplify this a little bit. All we do here is we pull out an r, right? And this is what a polar imaginary number will look like, okay? Basically, here's the general rule. In polar form, the polar form of a complex number, a plus bi, is nothing more, and all we do is we put the I in front. It looks a little bit better than put the I at the end. It just looks, same thing. It just makes it look a little bit prettier, right? Where R is going to equal cosine of an angle plus I sine of the angle, okay? Again, R is going to be the square root of a squared plus b squared, and yes, we're going to use that tangent, or basically the inverse tangent of b over a to find the angle, just like we did before, okay? When we took points and put them in polar form, all we really used to find the radius was the Pythagorean theorem. We're doing the same thing. In order to find the angle, we're still just using the inverse tangent, just like we did before. Okay, but this is the general form. Now, this is standard form. Okay, it's kind of a long way to write one number. So we actually do have what we call a shorthand here. It's not something that is standard per se, but it's kind of I look at it as, almost a shorthand kind of thing, where if you take the number 4 times cosine of any angle, 120 degrees, plus I sine of 120 degrees, right? This is an example of a polar imaginary number. This is a long number. Well, the shorthand version is we need the 4. That's the radius. We need that thing, right? And you know how earlier in this year we had to write all those sine, cosine, tangent, sine, or cosecant, secant, and you guys all it got to be a lot of writing. Well, that's basically what we do. Is we take that c out of the cosine. We go, all right, well, we need that c, but we all know it's cosine, so we can kind of get rid of the os. And well, we definitely need the I, right? And then we need the S, but we all know it's sine, the rest of that. And we don't really need to write 120 twice, so we'll just write it once. This means the same thing as that whole thing, okay? for CIS 120 means 4 times the quantity of cosine of 120 plus I sine of 120. They mean the exact same thing. This is kind of, shorthand for that long number. Okay. All right. So let's try some examples here. Here's really what we're going to start looking at. So what we need to be able to do is be able to take a rectangular number and put it into polar form. We got to turn this down here, this 1 plus I, into something that looks like this. Again, the idea here, that 1 plus I, we'd be going right 1 and up 1, right? So there's where that point is. So there's our vector going out to that point. We need to know the direction, the angle, and the radius. Well, to find the r, we're just going to use the square root of a squared plus the b. There is a 1 attached to that, right? Okay, that's how we're going to find the r, which would just be r is going to equal the square root of 1 plus 1, or 2. So we get r is equal to the square root of 2. And then to find the angle, we're just going to use the b over a. So 1 over 1, which is 1. When does tangent